Greetings, this is Jordan. I'm in a group with Clayton and Minucci. Our topic is partial fraction decomposition and log growth. So we're working on the BC Calculus free response question number 5 from 2004. There's no free response questions that deal explicitly with partial fraction decomposition. So this one is all log growth. But within your free responses, you'll obviously most likely need to use partial fraction decomposition at some point in time. So with that said, the question asks or states a population is modeled by a function p that satisfies the logistic differential equation that I am going to write here. So we have dp over dt equals p over 5 times 1 minus p over 12. So this is what's given. The standard differential or logistic differential equation is dp over dt equals k, which is a constant of proportionality, p, which obviously represents your population, 1 minus p over m, where m is the carrying capacity. So part A, the first part asks if p of 0 equals 3, what is the limit as t approaches infinity of p of t? So limit as t approaches infinity p of t. And there's actually two parts. It says the same thing with p of 0 equal to 20. So at first I thought you're going to have to integrate. In fact, you don't have to integrate because of this. Your what's it called? Your carrying capacity. Yeah, m is your carrying capacity. So if you kind of think of it simply as time goes on forever, you're going to really approach this carrying capacity regardless of the initial population. So if your initial population is greater than your carrying capacity, then you're going to have a decrease in population. You're going to have a decreasing population, and if your initial population is less than your carrying capacity, it's going to start to grow. So for both answers, you really don't even have to do any math. You can write just limit as t approaches infinity of p of t equals m, the carrying capacity, equals 12. Right, and then you'd write it again for the second case here. Now, if you didn't know this, you could of course integrate it, but it's not necessary if you're aware that the carrying capacity is the limit of the population as time goes on forever. So that's part A. Alright, so for part B, we're still working with this differential equation that we used in part A. dp over dt equals p over 5 times 1 minus p over 12. And we, I showed you in the last part that dp dt equals kp, which is constant proportionality, times 1 minus p over m. This is the standard equation for standard differential equation for log growth, where m is your carrying capacity. So obviously in this case m equals 12. And part B is asking if p of 0 equals 3, meaning, and anytime you see p of 0, that's referring to your initial population. So if p of 0 equals 3, for what value of p is the population growing the fastest? And I thought overall this was a fairly easy free response, but I thought this part was particularly easy because, again, kind of like part A, you don't have to do much work if you know that the population is always growing fastest when the population is 1/2 of the carrying capacity. So I'll go ahead and write that. Population growing fastest when P equals 1/2 M. So in this case, population equals 1/2 M, which is 12, equals 6. So there's your answer. The population is growing fastest was when P equals 6. And if you look along at the AP score line, they literally write the same thing. But if you didn't know that, the population was the population is always going to be growing fastest when it is equal to 1/2 of your carrying capacity, you could have just taken the derivative here of this function given, and set that equal to 0 and solved for that. So again, a pretty easy part B. Alright, so part C here, I think it's probably easily the hardest part of the problem, but still certainly doable. So we're given a new population. We're given its differential growth equation. So we have dy over dt equals y over 5 times 1 minus t over 12. Alright, and I'll go ahead, over 12. I'll go ahead and write the standard equation here. Alright, so again, in this case we have a constant of proportionality k equal to 1/5, and our carrying capacity is 12. The question is asking to find y of t if y of 0 equals 3. So find y of t when y of 0 equals 3. So we're just going to have to separate our variables, integrate, and then use our initial condition here to solve for our constant. So when we start integrating, we get, we'll split up our variables. We'll have 1 over y dy equals 1/5 1 minus 1 minus 12, 1 over 12 dt. We'll integrate each side, and we'll end up with the natural log absolute value of y is equal to t over 5 minus t squared over 120 plus c. So this is what we have to solve for, and we have our initial condition here. So the easiest thing to do here is simply say that the natural log of y, which is in this case 3, equals 0 over 5 minus 0 squared over 120 equals c. These go away, and you're left with c is equal to the natural log of 3. So now to solve for y of t, let me just do something new here. We simply, well, here we have our equation here. We'll have to exponentiate to solve. So really we have, if we bring this over, we'll have the natural log y is equal to t over 5 minus t squared over 120 plus our constant, which is the natural log of 3. Exponentiate, and we end up with y is equal to e to all of this here. So t over 5 minus t squared over 120 plus the natural log of 3. And of course, when you have e to the natural log of anything, we can rewrite it as this. And there you are. This is your final answer. Y of t equals 3 times e to the t over 5 minus t squared over 120. Again, we used our differential equation here with our initial condition. We separated our variables here. We integrated, solved for c using our initial condition, and then rewrote the equation in terms of t, and that should get us all 5 points there. Alright, so finally we're on part D here. Part D asks, for the function y found in part C, what is the limit as t approaches infinity of y of t? So I've written the function and the limit here. You may be tempted to plug in infinity and say 3e infinity over 5 minus infinity squared over 120. You may be tempted to do that, but you end up getting an indeterminate with the infinity minus infinity, so that doesn't work. So what you have to do is look at the original growth function given to you in the problem, which I'm writing. Oops, that's a t over 12. If you look at where the function, this function, if you look where it's increasing and decreasing according to this, its derivative here, if you look at where it's increasing and decreasing, it's increasing from 0 to 12. Alright, so the population is growing between 0 and 12t, whatever the time units might be in this particular problem. It's decreasing from 12 to infinity. Oops. Alright, so if you evaluate the limit of this function as it approaches infinity, it'll increase from 0 to 12, but then from 12 to infinity, it's decreasing, so the limit is ultimately 0. And this, oops, that's your answer. The way the scoring was set up on this one, there was nothing you really needed to show. There was just 1 point for answer. So there you go. That is 2004 AP Calculus BC, question number 5, parts A, B, C, and D.